Okay, we do have one small problem when we're working with log equations, and that is that the domain of the log function contains only positive numbers. Now, when we're only working with one logarithm, that's not a problem, because the range of the inverse, the exponential, only contains positive numbers as well. So we're just not going to get negative numbers for the argument of our log. However, if we multiply or divide two negative numbers, the result is positive. So when we combine logs, we risk introducing extraneous solutions. Remember, our log rules say, as long as both of the arguments are positive, the log of the product is equal to the sum of the logs. The log of the quotient is equal to the difference of the logs. If the arguments are both negative, well, the whole thing is just undefined. So here's an example where we're going to get an extraneous solution when we solve. We have one log expression, two log expressions, and a constant. So we start with our original equation, and we start by adding log base 4 of x minus 5 to both sides in order to collect all the log terms on the left. And then we have a sum of logs that's equal to the log of the product. So we'll have the log base 4 of the product x plus 7 times x minus 5. And now we have a single log equals a number. We can rewrite that equation in exponential form. So on the left, we'll have the argument of the log, x plus 7 times x minus 5. The base stays 4, and we have 4 to the third, which arithmetic tells us is 64. And now we can solve this equation, right? We have something factored equals a number, which is not 0, which means that we need to multiply it out, get everything on one side, and then refactor. So we've got x squared plus 2x minus 35 equals 64. Subtract 64 from both sides, x squared plus 2x minus 99 equals 0. And now this is a quadratic. Its leading term is 1, so we can use the shortcut. We're looking for two numbers whose product is negative 99 and whose sum is positive 2. That's positive 11 and negative 9. So we have two solutions here, x equals negative 11 or x equals positive 9. Okay, so those are the solutions that we got in the solving process, but it might be that one or both of them is extraneous. To identify the extraneous solutions, we just go back and plug into the original equation. And if we have an extraneous solution, one or more of the logs will be undefined. So with x equals negative 11, we have the log base 4 of negative 11 plus 7 would be the log base 4 of negative 4. Oh, that's undefined. So x equals negative 11 is an extraneous solution. We also have x equals 9, in which case the left-hand side is the log base 4 of 9 plus 7. That's the log base 4 of 16, we know that 16 is 4 squared. So the log base 4 of 16 is 2. On the right, we have 3 minus the log base 4 of 9 minus 5. So that's 3 minus the log base 4 of 4. The log base 4 of 4, the log base anything of the thing, is 1. So this is 3 minus 1 is 2. Those are actually equal. We have a true solution in x equals 9. There's actually only one solution to our original equation. Notice that the extraneous solution we got was not in the domain of one of the log functions. So rather than going back and plugging in at the end, we could also note the restrictions on x up front. So we need x plus 7 to be greater than 0. That means x needs to be greater than negative 7. We also need x minus 5 to be greater than 0. That's the other argument of a log. So we need x to be greater than 5. We need both of these to be true. But if x is greater than 5, it's for free greater than negative 7. Or we could think in terms of the number line, as we did for compound inequalities in the past. Either way, we could have gone in knowing that only solutions where x is greater than 5 would be true solutions. If we had done that work up front, we would have known as soon as they turned up that x equals negative 11 is extraneous, but x equals 9 is a true solution. You can discard the extraneous solutions either way, either by noting the domain up front or by checking them at the end. Either one is a correct method here.